In Chapter 7, Part 2 of 3, we want to see how to find the potential function. Now, if you have a look at this differential equation on the left, you notice here is what we call m and n. The partial of m with respect to y would be 3y squared. The partial of n with respect to x would be 3y squared. So it is indeed in exact form, and we're told that the potential function is xy to the third. Now, the purpose of this part 2 is to show you how in the world we come up with that, but first I want to show you the significance of that. In the first part, I showed you from the chain rule how we can recover the phi, and it just comes out to be the constant. So if we know what phi is, we can get the solution just by setting that equal to the constant. Now, since we're trying to recover y as a function of x, we'll try solving that for y. Let me show you again. Now, I'm not going to prove that this is in exact form. However, again, if this is exact form, which it is, and this is the potential function, which it is, that simply means that the solution is this. The potential function equals some constant. So that's the power of exact form. If we know the potential function, we basically have the solution. And of course, we do want to try solving for y as best we can. And again, here's the differential equation in exact form. Here's the potential function. The potential function equal to c is the answer. Now, you notice here we've got a y squared and we have a y cubed. We're not going to solve for y in this one. Again, from this differential equation, if we know the potential function, we have our solution. And just like before, since we have a y cubed and a y times ln of x, we're not going to bother trying to recover the function. So here are the steps for finding the potential function. I'll show you how to use those. So let's take this differential equation, which is in exact form, and see how we go about recovering the potential function. Well, it's based on the idea that the m is the partial of the potential function with respect to x, and the n is the partial of the potential function with respect to y. And so we're just going to write them in partial form. We're going to choose one of those, it doesn't really matter which, and integrate. For example, if we choose the partial of phi with respect to x, we want to integrate that with respect to x. Now, had we chose the partial with respect to y, we'd want to integrate that with respect to y. So we'll integrate this with respect to x. The integral on the right of 2xy with respect to x would be, if we bring down the 2 and the y, the power rule, x squared over 2, gives us x squared y. On the left, when we integrate the derivative of phi with respect to x, we get just the phi. Now remember from Calculus 3 that when you integrate with multiple variables, if we're integrating with respect to x, then our constant of integration is going to be some function of y. Now that function may turn out to be just a constant, but if we're integrating with respect to x, y itself could be a constant. So here is the integral with respect to x, and we've partially recovered our potential function. To finish it out, what we're going to do is we're going to do the partial derivative of this with respect to y. We just integrated with respect to x. Now we're going to do the partial with respect to the other variable, which is y. So doing the derivative of phi with respect to y, doing the derivative of x squared y with respect to y, and then doing the derivative of h with respect to y, here's what we come up with. Now the next thing we want to do is to combine these two together. Since we're told in the beginning, we knew that n was the partial of phi with respect to y, and right here we have the partial of phi with respect to y. We're simply going to put that in its place and then set them equal to each other. So here's the two things that we set equal to each other, and then finish solving. If h prime is 2y, then we can recover h by doing the integral of that. So we end up then with the potential function from these two Now here's a differential equation that's in exact form. You can check that. And here's its potential function and the solution. Now, if we divided that differential equation by y squared, it should have the same solution. But this is not in exact form, so we're not able to find the solution. However, we can make it exact form by multiplying by y squared. Notice here I divided by the y squared. We can put that back in exact form by multiplying by the y squared. Now all that's doing is just illustrating to you that many things that are not in exact form can be put in exact form. Now, what we're going to do is see how can we put things that are not in exact form into exact form. We do that by finding the integrating factor. Here is the combination that allows us to find the integrating factor. You notice the integrating factor is much like the one that we used when we were solving linear first order equations. You might want to jot these down, and I'll explain to you how we use that. So here is a differential equation. You notice that if we do the derivative of m with respect to y and the derivative of n with respect to x, they are not the same. Therefore, it's not in exact form. Can we put it in exact form? Well, these are the two things that we would check. If either of these works out, then we can put it into exact form. So we just combine these two derivatives together in the right way. Starting with the one on the right, we're going to do the partial of n with respect to x minus the partial of m with respect to y, and divide that by m. Here's what we come out with. I'll simplify that as much as I can. And notice that this comes out with an x in it. So it is not a function of y. The only way it'd be a function of y is if it didn't have any x's in it. Here is the other one. If we do the other combination, here we take the partial of m with respect to y minus the partial of n with respect to x and divide it by n. So if that comes out to be a function of x, then we're in business. Combining these together and simplifying, notice the y squareds cancel, we come out with 2 over x. Now, since that only has an x in it, then it is a function of x. So all this is saying is if you come out with a function of x, then you can put it in exact form. If neither of these work out, then you cannot put it in exact form. Now, to put it in exact form, we find the integrating factor, which we'll call mu, just like we did before. Notice this time we're calling it a function of x. And it's the e to the integral of f of x, which in this case is the integral of 2 over x, which is 2 ln of x, which is the same as ln of x squared. And e to the ln of x squared comes out to be just x squared. Now what that means is we can multiply through by x squared, and our differential equation will be in exact form.